Hello, folks. Another day, another lecture. Today I was going to talk a little bit. I was really going to roast another dissident, and there were some loose ends that I absolutely needed to cover, and they have to do with this ether. Had to cross some T's and dot some I's, or maybe it's the other way around. Maybe I have to dot some T's and cross some I's. Anyways, the issue came up because there were some issues that were raised. Okay, and there's a listing of those. Uh, just in general terms, there were other issues as well, some other comments. I just wanted to make sure that we go over this before we move on. Okay, and the first one is that the Hillsters claim that theirs is not an ether theory, and that's what I said. It is. It's an ether theory, and then there were other people who, couple at least, that put comments and told me that they wonder or they ask if the rope model is an ether theory. We had a fractal woman a couple of weeks ago, and she said her ether is finite. She said it's like the direct sea, but the direct sea is infinite. So I don't know in what way her finite ether has anything to do with the direct sea, or how it can be an analogy, right? It can be used as an analogy. Ken Wheeler, he does ether with concepts, okay? Moves concepts around counter space and inertial and who knows what. Einstein, he gave a talk in 1920, Leiden University, and he said the general relativity cannot do without the ether. and, but he said his ether is different. Okay, ether is different than the traditional ether. That's what he was saying. Then we have Nobel Prize Robert Laughlin. In 2005, he wrote a book, and he says that today's mathematical physics establishment uses the ether, but they don't call it that because it's taboo. So what the hell is the ether? What in the world is the ether? That's what we need to figure out today. Now, uh, before I get into it, I just want to make sure we put it in the right context. I'm not going to be talking about what the ether does. I'm not going to be talking about verbs. I'm going to be talking about nouns. I'm going to be talking about what the ether is before we do anything with it, because that's where the problem is. That's 120% of the problem. Okay? The majority of these people say, "Oh no, mine is not an ether theory," or "Mine is an ether theory." And why do they come up with those labels? Well, they say, "See, mine behaves this way, and the other one behaves that way. So his is not, mine is," and they get into this talk. We don't care what the ether does. Does, verb. We care what the ether is, and that's what I'm going to talk about today, because everybody seems to skip that step and move on to what their ether does. That's where the problem's going to be. Okay, so I'm going to focus today on what the ether is, and a lot of people say, "Well, we all know what the ether is." No, we don't. That's where we have the problem. The problem is people don't understand what the ether is. Okay, and that's where we're headed today. Okay, so where did this word come from? Well, if we want to do a little history, we go back to the Greeks. Okay, they were the ones who came up with the ether, and one of the reasons they came up with the ether, in fact, I think the only reason, and it was because they were trying to explain light. What is this thing called light? How come we can see? Especially that they were trying to explain vision. They said, "How come I can see?" Well, what magic is this? Well, and they try to relate themselves to animals and so on. They said, "Well, animals also can see. So, what is this sight? What is this vision? What is this thing?" I mean, we can all understand a rock. Yeah, a rock, okay, I understand what that is. I understand what a tree is. I understand what a dog is, a house is, a cave. What is light? What is this thingy called that? Why can we see? What is vision? Especially that's what concerns them. Why can we see? And yeah, they associated the ether with light, and that's more or less where it has its beginnings. How did they envision it? Well, they envisioned it as a bunch of particles. That's what the ether was in their minds. It was the easiest thing that came to their mind. In fact, it's the first thing that comes to a person's mind. It's a no-brainer. It's like, oh yeah, there's a bunch of particles out there, and this is the easy. This is the where you spend no time on it, analyzing it. You just say, yeah, there's a bunch of particles out there, and let's continue. No, no, let's stay there for 2 years at least. Let's find out what the ether is, what these particles are before we do anything else. The other reason it has to do with, and why it's lasted so long, has to do with mathematics. To a mathematician, a particle is not a particle. And unless you understand that and really wrap your hands around that, you will not understand anything. A particle is not a particle. Okay? The word particle for a rational human being, anyone that's the street just stops and what's a particle? And he'll say, that's a grain of sand, it's a speck of dust, a little ball, a tiny bead. That's what everybody thinks when they hear the word particle. And that's not what it means to a mathematician. To a mathematician, it means a number. That's what it means. It means a number and a location for that number. So why did the particle hypothesis last until today? Because it's related to mathematics. You can pinpoint a solution, a value, a variable, a constant. It's a value, it's a number. And it's a single number. And that now becomes the particle. So to a mathematician, he's not thinking in physical terms. He's thinking that's a value that I've got there. You talk about a field. What is a field? A bunch of values. And the guy can go in there and say, okay, this little point over here, well, this one has a specific value because it's so far away from the center of mass, of charge, or whatever. And he said this one has a different value than the one closer to it. So that's what it means to him. That point, that dot he draws on the board, the dot is a representation of, so that he can more or less, or you can more or less follow what he's saying. But you're not supposed to think of that dot as a little bead. You're supposed to think of that as that's a point that represents a value, typically a number followed by a unit. If you're talking about gravity, it's maybe mass. If you're talking about charge, you're talking about something else. Okay? So that's why it lasted so long. And it's very comfortable for the mathematicians to think in those terms, and that's why the particle model will never die. It will never die because you kill all of mathematics, mathematical physics with quotation there. In other words, the way they see it, a particle is a value. That's all it is to a mathematician. And you're thinking maybe in physical terms, he's not. He's thinking in his numbers. That's why it lasted so long. And again, it was the first thing that came to the minds of the people of old, to the ancient folk. Did the Greeks come up with this first? No. If you go back in time, where do I have it here? You get this situation. You see all these gods that they had, and you can see the Greek gods appear maybe 1900 BC, thereabouts. Before that, you had the god of air, emptiness, in Shu, the Egyptian god. Before that, you had Enlil, the god of the Sumerians, the god of air of the Sumerians. That was around anywhere between 4,000 and 6,000 years ago. And maybe around the same times, you got the god of the wind of the Chinese and the god of the wind of the Japanese. So, the Greeks were not the first people to discuss the so-called ether. I'm sure that if you went 5,000 years ago, 3,000 years before Christ, 2,500 years before some of the Greeks who started this whole mess, Anaxagoras and was this Parmenides and so on. 2,500 years before that, people were already thinking about these things. And they probably had theories. They just were never written down. We've never received any of that information. But for sure, if they built pyramids, architects who were able to build that sophisticated building, There were probably researchers among them or theorists or whatever who looked at the night sky or breathed there and said, what am I breathing? What is this thing called light? They must have asked these questions. Okay. So I think that what happened, these things got passed down from region to region, generation to generation, and it finally ended up with the Greeks who started to analyze it in a formal way. Whether someone before then analyzed it in a formal way, the Egyptians who were quite advanced, the Sumerians, the Chinese, the Indians, I don't know, but you can count on that's probably what happened. Okay, so let's go back in time. What we have is that the ether was invented really to explain light. And to date, we've only had three proposals on the table throughout what we could call science, physics. I don't call some of most of what we do today physics, but just to label it, throughout history, throughout scientific physics history, we've had only three proposals. We had particles, we had waves, and we have the rope now, starting in the 21st century. Here they are. Let's put them up there. Okay, these were the different proposals. You can say that the particle ether theory started 2,500 years ago, you know, in the days 500 years before Christ. That's supposed to be 2,500 years, not before Christ, 500 years before Christ, sorry. 2,500 years ago, okay? And these are the Greek philosophers that tackled it. There were others. I just pulled four of them here because they're typical. We have Parmenides, and what did he come up with? He says the following. He says that there's two forms. There's darkness and light. There's light and blackness. Okay, that's what it is. What does he describe the ether as? A plenum of light. He's talking about an enclosure. What is a plenum? It's a container. That's all it is. What is a chamber? Chamber's got matter in it. So what was he thinking of? He was thinking that the universe was some kind of plenum, some kind of container, some kind of box or sphere, and it had all these little particles, just moving around in there. That's how he visualized light. Okay. Uh, about the same time, a little later, but around the same time, we have this fellow, Anaxagoras, and he's talking about smallness and unlimited. He's talking about an infinite sea of particles, essentially. And he says the ether covered all things. Okay, so you can see that they were discussing these things in those terms. That's what they had going through their minds. Plato, he goes a little more specific, and he says it's like the air, but it's a little different than the air because it's translucent. Okay, it's a translucid, and again, he picks this up from Parmenides essentially because he says there's the bright one, the light one, and there's the dark one. Okay, that's essentially what he says. And his student Aristotle, he disagrees quite a bit, essentially, with Plato, and he comes up and he writes, and he says, "Look, this thing is ungenerated. It's not created. It's already there. It's indestructible. So you can't. It's neither created nor destroyed. Already, he had that idea there. It's eternal, and it cannot be increased or diminished." Okay. And he put it beyond earth, fire, air, and water. In fact, he was saying that this stuff only exists outside of the earth, behind the moon. He said it exists only where the gods dwell. Only the gods are familiar with the ether. We don't have it here on earth. Okay, and he says it always runs. It was moving. It was in motion. So these were the ideas these people had of the ether. And what are we talking about? Well, we're talking about particles filling, the universe, essentially space, that black stuff you see out there every night. And you get to this point where you get to try to visualize what they were thinking about, and this is the best maybe I can come up with. You have the finite ether. You can imagine that any shape you want, or you can think of the infinite ether. Those were essentially the two proposals, and that was essentially the fight between these Greek philosophers. Some of them thought as the universe being infinite, space being infinite, and therefore since space was filled or made of ether, of particles, that sea of particles was also infinite. And others thought of it as finite, but fewer, I think. I think the infinite ether was more popular. That's my opinion on this, okay? Okay, um, so let's get me back up here. So, where did this take us? Well, this lasted for many centuries. In fact, you can say it lasted 2,000 years, from the 5th century BC to the 15th and 16th century, at least. And then in the 17th century, we have a little bit of a revolution. This generation of people, if you consider the whole century as a generation, they started to analyze some of the writings of Aristotle, especially Plato as well, but mainly Aristotle. And they started to do experiments, and they started to question some of the things that these people had in mind. And who were these folks? Well, I pulled out again just a few of them there. You can see we have Huygens and Newton, and later on in the 19th century, we get Fresnel, who's really a guy who put some seminal stuff out there, right? And of course, James Maxwell, who does a thorough mathematical analysis of essentially the ether. He's analyzing light, primarily light. He didn't do gravity so much. I don't even know if he did any gravity. He was so busy with light and magnetism and electricity that I don't think he branched off into anything else. At least I'm not aware of. And so the what were they analyzing? They were analyzing this thing that was in the background called the ether. Okay, so what does Mr. Huygens have to say about the ether? Well, he wrote, well, before him, I'm sorry, I didn't put him up there because there is no picture of this poor guy. His name is Robert Hooke. He's the guy who invents the wave nature of light. Okay. Now, some people, you might look on the internet and say, oh, look, Descartes already talked about it and so on. It's not true. I mean, I've gone through at least Descartes' main books, and you know he talks about vortices. He does talk about vortices. He doesn't mention the ether. He he talk in his books. He doesn't mention the word. He talks about Aristotle, and Aristotle talked about the ether. So he is referring to the ether, but he never mentions the word, but that's what he's talking about. But then he talks about all these whirlwinds, these tornadoes. He kind of came a little early for what some of these people believe today, that all these particles are some kind of vibration whirlwinds out there, you know. So he already had that idea. That's in his book. So Descartes talks about, you know, the vortices. But the guy who comes up with it, Robert Hooke, and the reason we don't have a picture of him today is that he was an enemy of Newton, and Newton was a deadly enemy of Robert Hooke. They hated each other's guts. Robert Hooke was a right-hand man to Robert Boyle. Robert Boyle was blue blood. He's the guy who essentially created and was the most influential person in what is known as the Royal Society. Royal Society was maintained by the King of England. Charles II had come back after Cromwell and his son were kicked out of there, and the Puritans. And you know that's when they approached Charles II, and he decided to send some money to this new enterprise called the Royal Society. That's when the Royal Society started. And they started looking at vacuum, and they started looking at light. And so Robert Boyle was a very influential guy. He was the guy who had the king's ear because he was blue blood. Robert Hooke was a poor guy. You know, he was just Robert Boyle's right-hand man. He was the guy who did the experiments for Robert Boyle. Robert Boyle was the theorist, the guy who wrote about it. Okay. And so, not so much, I don't think Robert Boyle had a problem with Newton, but Robert Hooke hated his guts, and vice versa. And so Newton never joined the Royal Society until Robert Hooke was dead. The year that he was dead, Newton came in and he took over. He became the head of the Royal Society. And the first thing that Newton did was take the only picture available of Robert Hooke and burned it or threw it away. So we don't have any pictures of Robert Hooke. But here's what Robert had to say, and this is from his book. He published it in 1665, and you can see he's the first guy who comes up with the wave nature. You'll see it everywhere. You'll see the word wave everywhere there. And what is he talking about? He's talking about the wave of what? Of the ether. Okay, that's what he's talking about. He says it's a medium, it's a fluid body. Okay, and he's talking about particles. He's talking about the fact that these bodies, these parts of bodies, are loose from one another. What does he describe me? He's describing a whole bunch of particles. That's it. Okay, it's no more science than that. Okay, and then we have this gentleman. His name is Huygens. He's from Holland. See if I can put him up here. And Huygens also, he comes a little later with his book 1690, and he says, he talks about, again, the waves. He's the guy who analyzes the wave. He analyzes the spherical waves. He's thinking longitudinally as sound, because he does make reference to sound. So he's in between, all these waves. He's got a wavy brain. Okay, that's what he's got in his head. What is he talking about? He's talking about the particles of the ether. Okay, he's talking about fluid matter. Okay, so this is what they were visualized. This is what was going through their mind. This was the medium that was going to be vibrating, waving. Okay. And Newton, you would think that he was against the ether. No, he was an ether guy as well. The issues between Huygens and there was a little tete-a-tete, and there was also fight between Newton and Hooke, who defended Huygens' version. He says in a letter to Robert Boyle, 1678, okay, he says, I suppose that there is diffused through all places an ethereal substance. I suppose this ether pervades all gross bodies, okay? And he's talking about little particles. And his concern was only that, these, he could not imagine these things vibrating up and down as they were. He was thinking of transverse waves, even though he didn't really come across that concept. That would have to wait until Augustin Fresnel in the 19th century. But this is essentially what was going through his mind. He could not visualize a wavy thing, as Hooke and Huygens were proposing, imitating light. How could light travels straight, he says, and these guys are saying that it vibrates up and down? He could not imagine that. And so this was his objection. But Newton also dealt with the ether. Every analyst in the 17th century, they all believed in the ether. They believed in the ether until today, in fact, all the way to today. More so in the 19th century, but all the way to today, everybody believes in the ether. In fact, today, everyone believes in the ether. I'm going to go over that in a sec. But, this is what they had in mind. They had a bunch of little particles that either were vibrating or going straight, but it was all particles. It was a particle world. We never abandoned the particle world, even when we introduced the wave. And some people say, well, Bill, you're full of it. A wave is a little different. Looks, like if you take Maxwell's wave, which I'm going to get into a second. Let's see if I can find it here. It looks more or less like this. Okay, but see, what are we staring at? We're looking at vectors. That's not an object. That's not a physical object you're staring at. That's a mathematical contraption. That's what that is. And what you're staring at is a bunch of vectors. Those red and blue arrows, they're vectors. They have magnitude and direction. This is only numbers that are moving there. There is no physical object called a transverse wave. Something else is what's doing the waving. You have to identify the kangaroo and not talk about, the jumping kangaroo. That's what these people did. And they bypassed the object. But if you put them against the wall and say, well, what is the object? It would tell you, oh, it's a bunch of particles. Newton would tell you that. Huygens would tell you that. Hooke would tell you that. Robert Boyle would tell you that. All these guys dealt with particles. It was a particle world, and it still is. Nothing has changed really in 3,000 years. Okay. Okay. Let's put this back up before I lose it. Sometimes I lose these little things. I want to leave that up there. Okay. So what were these guys describing? Well, they were describing something that looks like this. Let's see if I can put it up here. The only question was whether it traveled straight or waved. I don't know if you see the one on the bottom there, the blue one that's going across. That's supposedly the straight um, wave or the straight light that Newton was thinking of going through the ether. And the one on the top is the one that Huygens and Hooke were thinking of. And that's essentially what I discussed the other day with the Hillsters. They were thinking they're thinking of the same thing. They're saying that the one on the top can be represented, or the analogy for it can be put with your massage in the shower cap, the massage portion where it waves up and down. And the one on the bottom is when you turn just your regular shower on, all the drops of water go straight. And they say theirs is the one that goes straight, but on the other hand, they say the G1 does vibrate, so it's like the one on the top. And what is vibrating? And they're saying was the G1 particle, and they make it clear that their particles fill all of space. And so they're talking about an ether, whether they like it or not. That is the ether, because before they wave anything, before they move anything, we have to identify what the ether is. And the ether is a bunch of particles. And you can use the one that the Greeks had in their mind. Let's see if I can put that back up there again so we can have it clear. Where is it? This one here. Those are the choices. We don't have anything moving because motion seems to confuse all these people. Okay? That's the ether. Now you can choose whether your ether is finite or it's infinite. Okay? Which one do you want? That's it. Before you move anything, before any of those particles move. Okay? And so this is the problem. These people want to move directly to this thing here. Let's see if I can put it back up there. They want to move directly into that, and that's not allowed. Okay, they shouldn't be allowed to move to the dynamic ether. They have to first tell us what the ether is before they move absolutely anything. Okay, so that's the issue. Okay, the question is, if it's a bunch of particles, why are they moving? Also, because here we have a sandbox. Is that what the ether is? Just a bunch of particles? Why are they moving? Why are they waving? Shouldn't it be a static sandbox out there? And if it's a sandbox, why can anything go through it? Can you imagine a ball trying the earth going through a sandbox? So this is something you got to keep in mind, that if the ether is just a bunch of particles, why are they moving? What causes them to move? And even if you don't want to explain that, you say, well, they're just moving. Okay, so you grant it. But the question is, do they move just back and forth locally? Do they move across the universe? What kind of motion do these things have? And if they move across the universe, why? Then you have to explain why. If they move locally, well, you can say another one pushes on it and they're all moving against each other. That we can all more or less comprehend. But if you say that this ether particle moves across the universe in some kind of direction, then you have to explain that motion. You have to justify that motion. You can't just get away with it just, with your magic wand. Okay, so this is what we had all the way till the 19th century. In fact, if you go in there, you'll find Mr. Fresnel, and he comes up with the transverse waves. Okay, he did I put longitudinal waves? Why did I put longitudinal waves? I guess that's when, because he was proposing longitudinal waves in 1819. It wasn't until 1821, 2 years later, that he comes up with a transverse wave. Okay, so until 1819, he was still thinking of longitudinal waves. Okay, but the important thing is what he says about the ether here, because that's what we're analyzing. Light consists in vibrations of the ether. What is the ether? An elastic fluid. What is it made of? The particles. Okay, straightforward. And then he's just going to go in there with transverse waves. And they were all aware. They were all aware in the 19th century that somehow transverse wave had a hard time going through fluids. So they had a contradiction. On the one hand, they said, well, transverse waves is what light is, the medium is the ether is fluid, but transverse waves cannot go through fluids. And so they had this circular contradiction. Okay, and they realized that. They were all aware of this. Okay, and this problem persists till today, and that's one of the reasons people of the establishment have rejected the ether, because they say, look, if it's the ether, and we're going to talk about waves, most of the distance are wave theorists, you can't send a transverse wave through a fluid. And that's the key issue. That's at least one of the key issues. The other one is obviously the supposed um, debunking of the ether by Michelson Morley in what was it, 1887. Okay, we had in the 19th century, just shortly after Fresnel, about 20 years later, we have Mr. Stokes, and he was the head of the Royal Society. And he proposed also, he says, I shall suppose that the earth and planets carry a portion of the ether along with them, so that the ether close to their surfaces is at rest relatively or to those surfaces, while its velocity alters as we recede from the surface, till at no great distance it is at rest in space. According to the undulatory theory, the direction in which a heavenly body is seen is normal to the fronts of the waves which have emanated from it and which have reached the neighborhood of the observer, the ether near him being supposed to be at rest relatively to him. If the ether in space were at rest, the front of a wave of light at any instant being given, its front at any figure time could be found by the method explained by Airy's track. Okay, talking about Airy, who was another British physicist. If the ether were in motion and the velocity of propagation of light were infinitely small, the wave's front would be displaced as a surface of particles of the ether. Neither of these suppositions is, however, true, for the ether moves while light is propagated through it. So here he's distinguishing, as you can see, the ether from light. He's saying, you know, light is something that goes through the ether. So what the hell do we need the ether for? I mean, if light goes through it. We thought that it was the vibration of the ether. And you can see that this is where a lot of people get confused today. Because when you attack one guy, says, no, mine is not an ether theory. And he's referring to one behavior of the ether. The other guy says, oh, mine is an ether theory, because he's referring to another aspect of the behavior of the ether. None of them are addressing what the ether is. A bunch of particles. That's the definition of ether. Bunch of particles, many particles. Anyone who proposes particles is proposing an ether theory, whether he knows it or not. What his particles do, we're not concerned about. Not yet. We'll get that in 2 years, okay? Right now, we're trying to figure out what the ether is, because that's where people have problems. They all want to skip that step, and they want to move directly into what the ether does. That's where the problem comes in. And we're not going to deal with what it does. We want to find out what the ether is before we do put any motion in there, because that's where, you know, people have not agreed to what the ether is yet. We have to identify what the ether is, and that's where I'm headed. Okay, shortly after Stokes, we've got first Mr. Maxwell, and a few years later we have Einstein. And what does Maxwell propose? Well, he proposes, or he analyzes, essentially the luminiferous ether. That's what everyone in the 19th century was thinking about. Okay, and what was he thinking? That's out of the Wikipedia. It summarizes what all these people believed in. A medium for the propagation of light. According to Robert Boyle, this is from the Wikipedia again, the ether consists of subtle particles. What is the ether? A bunch of particles. Anyone proposing particles in any way, shape, or form has an ether theory. Okay? I don't care if they vibrate them, if they push them around, they say mine goes straight instead of crooked. I don't care anything about that. What we're talking about, what the ether is, we're looking at the noun and not the verb. Okay? And according to Einstein, in 1920, he gave a little speech. He says, according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, there exists an ether. Yeah, those words come from Einstein. Okay? According to the general theory of relativity, space without ether is unthinkable. Those words come from Einstein. For in such space, there not only would be no propagation of light, but this ether may not be thought of as endowed with a quality characteristic of ponderable media. He's saying that well, let's continue here. As consisting of parts which may be tracked through time, the idea of motion may not be applied to it. Einstein is saying that there's all these particles out there, okay, but they're you know it's made of parts, but they cannot be tracked somehow. We have no way of touching them, but it's made of parts. But these parts don't move, and they don't weigh anything, and they don't have any mass. That's essentially what he's saying. He's saying, my ether is just some kind of background. I'm not even sure what purpose his ether serves if it's not going to do anything with light. It's not going to move. It's just a background there. He's talking about a sandbox. That's what he's describing, a sandbox. And he's saying the earth, the moon, everything moves through the sandbox. You figure it out. Okay. Okay, so this is where all these people were headed. Who came next? Well, we have another fellow, and he's from the quantum group. He starts with quantum, and that's after the 1920s when quantum really took shape. Okay. And these are quantum guys. Even the guy on the bottom is a quantum guy today, but they have to be careful, otherwise they lose their gold medals. And Paul Dirac came out with a Dirac sea. What is the Dirac sea? An ether theory. That's what it is. Here's from the Wikipedia again, a summary of what Paul Dirac proposed in 1930: an infinite sea of particles with negative energy, filling all of space. Okay, so he's talking about the space being filled. Space is a container that is filled with particles. Okay, that's his idea of the ether. And he was rejected by his colleagues. Nobody ever paid attention to his Dirac sea. It died. And then we have Laughlin, Robert Laughlin. He's a Nobel Prize winner, and he's got to be careful. I put Laughlin 2 times here. Okay, one little error. You can kill me for that. He says the modern concept of the vacuum of space, confirmed every day by experiment, is a relativistic ether. He's again bringing Einstein into the game, but we do not call it this because it is taboo. Okay, so these people are worried what their colleagues are going to say about them. They're put this one back up here. They're worried about what their colleagues are going to say about them. If you say, "Oh, the ether, that's a 4-letter word." You can't bring the ether today because it's already been debunked. But what is quantum mechanics? Quantum mechanics is an ether theory. What is space according to quantum mechanics? Okay, not according to me. According to quantum mechanics, space is made of particles. It's made of or filled with particles. In that case, you don't have to define what space is according to them because they say it's made of particles. Okay, so what contours each particle? What are you going to say? Space? What's the background to each particle? And then they say, well, no, see, and they turn it into a fuzzy thing so that you cannot even imagine. It's a vibration of fields, it's energy, it's virtual particles that are in there. Virtual means that it comes out of a magic wand, that it comes out when the mathematician needs to explain something he saw in the lab which he cannot explain rationally. And so he said, oh, the particle came from space. What do you mean space? When it came in, did it leave a hole behind? What's that hole? Space? What is space? Well, it's made of particles. So we get this runaround. That's the problem. The problem today is the ether. The problem is space. It's always been space. No one could figure out space. We could all figure out the things we could see and touch and smell and hear. We cannot figure out the things that we see, but we see indirectly. We can't see gravity. We can't see the mediator of light. We can't see the mediator of magnetism, electricity. And so we invented this ether, there's something there. There's some particle there, something. That's the best they could come up with. And well, this takes us to our the folks that we have today. And we have Aetherists. One of them is a fellow I've been talking about the other day. And that's Mr. Wheeler. And he's got this ether. He's got all these concepts as ether. Okay, he tries to explain magnetic field, and he uses these fancy words, the centripetal and the centrifugal, and what are those? Well, those are motions. Those are flows. Flows of what? Well, he doesn't believe in particles, so I guess what's flowing is concepts. Okay, so he's got all these concepts, counter spatial and inertia and radio and whatever. All these are concepts. So Wheeler's not a physicist. He's not doing physics. What he's doing is really nonsense, because what he's proposing essentially is that he can do physics with concepts. He's going to move concepts around. He's going to talk about the flow of flows or the movement of movement. And that's all these what these words are: dielectricity, counter space. There's no physical objects called counter space. There's no standalone physical object called dielectricity. So you can't say dielectricity did this and counter space did that. You can't say that. Not in physics. Maybe in religion you can, over there in Sunday school. Not in physics. And then we have these the Hillsters. Okay, and they came up with this particle world. They claim that that's all there is, just particles. They say it clearly. The particle model is a physical model of the universe. That is, all areas of physics can be explained using physical interactions of particles. And he said gravity, light, etc., it can be explained using particles. Okay, I think it's straightforward. He's talking about a particle world, and on the right you see the particles they're referring to. They call them the G1, G2, the N1, the N2s, and so on. And he adds it's based on particles which don't exist. And I really hope he was joking there. I cannot imagine him having said that, but if he really means that, then it's total nonsense. It's poppycock. That's what it is. Anyone who proposes unreal particles, especially when it contradicts the Hillster's definition of real exists, he says objects that move. Well, if the G1 is a particle and it moves, it's real, according to the definition. And so David is coming in there and saying, well, it's a particle that doesn't exist, which is a contradiction with the definition. Anyways, this is an ether. What you're staring at there is the ether, and the only thing anyone has to explain who proposes particles is the black stuff. What the hell is the black stuff? And they should spend 2 years analyzing what the black stuff is. Now, some people with very little brains, I call them pea brains because that term comes from string theory. I think it is applicable to them. They say, well, space or nothing is that which is not something, or that which lacks something, or that from which something was removed. That's an irrational definition. We don't use antonyms or synonyms to define crucial terms. Okay, so you cannot say that nothing is the absence of something. Not in physics, at least. You cannot get away with that in physics. Okay, you should be able to define it with words that do not include synonyms or antonyms. You cannot say, what's a dog? Well, a dog is not a horse. Well, no kidding. Is it not a house? Yeah, it's also not a house, and not a rock, not a tree. You're going to go through the whole list of what it's not? No, that's not a definition. No, you got to define it properly, and that's why the people who skip that step, because they say, well, you're doing semantics, Bill. You're doing ontology. You're doing word wizardry and word games. We're talking about the foundations of physics. You have to define what something is when nothing is, and it's got to be precise in such a way that you can use it consistently, right? So that you can make your point and that people can follow your presentation. If you don't define the word nothing, the word space, the word vacuum, and you define it loosely and say, well, you know what I mean, nah. Now, those are words that you absolutely must define if you're going to do physics. Anyone who can't define those words is not a physicist, period. That's simply the way it is. Okay, here we have the way the Hillsters proposed gravity, and which is, again, this is a Lesage theory. It comes all the way from Fatio, guy that was Newton's right-hand man. It comes even before then from people like Descartes and Gassendi, Pierre Gassendi, who wrote a book about this exact model, the shadow model. And the shadow model is on the bottom there, bottom right. What you have is fewer particles between the two balls, the two blue balls. And the blue arrows indicate that there's fewer particles. And then the red arrows more stronger or more particles coming from the outside pushing the two objects together. Why? Because one object shadows the red particles or red arrows, the flow of particles from that region shadows it from the other object. That's what it is. And so this is a push gravity idea. What were the problems? Well, you can see it on the top. That already pretty much exposes what the problem is. If there are more particles entering the any object in the universe, all objects, in fact, then that blue ball on the top should be bloating like a smoking toad. It should be bloating. It should be getting bigger every second. And the same with every object in the universe. Every star should be getting bigger. And none of them should be sending things out. They should all be receiving more particles than they send out. They're depleting the universe of particles, essentially, of the ether. Okay, so I don't know. I don't know how they're going to fix that in their book. Okay, and what's the other problem that they had? The other one was the, where is it here, if I can find it? Got so many of these sometimes. Okay, the magnetic version of their magnetic proposal. It looks something like this. Let's put this back up here. Okay, and boo, I missed. Here it is. Okay, so what do we have here? Well, we have, again, what you have is that these people are doing magnetism with particles. With the same particles, they do gravity because they say magnetism is a gravitational phenomenon. On the top, you see the G1 particles, those blue ones. Those are going in because they have to explain gravity, and they have to go to the center of gravity of the magnet. Okay, so that's in the background. Okay. Meanwhile, you can see the I don't know if you can see those orange little lines going around. Well, that's the magnetic field, sweeping around the magnet. So that's it. So the magnet has the magnetic field going around it, and then you have the gravitational G1 particles coming towards the magnet, towards the center of gravity of the magnet. That's gravity. That's in the background while the magnet is working. Okay, so now on the bottom you see the magnet again, but this time they have the G2 particles hitting the edge of the magnetic field and stopping there for some reason, because they say the G2 particles also go all the way to the center, but for some reason, they stop also at the surface of the magnetic field. And the problem there, one of the problems is that the magnetic field extends farther than what the iron filings tell us. That's one issue. The other issue is, this is quite ad hoc. The folks here, the Aetherists are saying, we have the G2 just stop at the edge to explain the pattern that we see in magnets. And then the other issue is that G1s, they go around, and they go through the center of the magnet. They use the G1, as you can see on the top, they go straight when they need gravity, and then they have them curving around when they need it to go through the center of the magnet. And of course, one of the big problems with this whole scenario is that if this were true, okay, if this is the way Mother Nature runs her shop, the iron filings should accumulate in the center of a magnet. And as we saw the other day, no, they don't. Iron filings accumulate at the north and south ends of a magnet. So I don't know how they're going to explain that. Maybe they have some kind of explanation for that. I think these are fatal flaws in their model. Okay. And so what can we say about the ether? Well, I think that we have to do the following. We have to analyze the ether rationally, and I'm going to put up a little flow for those rational folk out there who want to criticize anyone who comes up with ether. You can follow this chart. I'm going to put three things, one right after another, to show you what questions to ask of an Aetherist, anyone who proposes particles, okay? Anyone who proposes particles in any way, shape, or form, whether it's quantum mechanics, the so-called non-Aetherists like the Aetherists, those who vouch for the ether and never explain what it is or describe what it is, okay? And these are the questions. Okay, this is the flow of reasoning. Okay, that I want to put up there. And it starts like this. We have the definition of the word ether, right? What is the ether? Well, in physics, it is mandatory to define the words that make or break your theory. Okay, let's start there. If you have a word such as, I don't know, particle, and you don't know what a particle is, well, and you're giving the presentation, people can't follow you because they don't know what the word particle means. You can't define it or you can't draw it or whatever. Well, then we got a problem. You better know what a particle is if you have a particle theory. You should be able to illustrate if it's an object. If you're using a concept such as, well, it's a vibration of a field or it's a bunch of energy, a lump of energy, then it's a definition you need for that. Okay, so you either draw it or you define it. That's it. There's no other choice. This is not an issue of word games, ontology, philosophy, or semantics. It's got to do with the foundations of physics. Every discipline has a foundation. If you're going to study law, you better know some words that are the foundations of law. If you're going to study medicine, you have to have the foundations for words, yeah, for medicine, which include the words. You know, you're not going to talk about ether, maybe, in medicine or in law. That's not part of their foundations. But particles, if they're objects, well, yeah, then objects you have to define for the purposes of physics. You have to define what a thing is, what a nothing is. You got to define these terms. You got to define distance. You got to define exist, because physics is the science of existence. It only studies that which exists. You got to define these terms, not because you're doing semantics, not because you say, well, you're going too far. You're going with word wizardry, word games, etc. No, it's got to do with laying the foundations. Okay, and then again, it is an issue of establishing the foundations. Concepts we define, objects we point to. Okay, very simple. You come to the conference and you present whatever conference, I don't care. You present the monkey. And you say, "This is a monkey." Okay, so you present the thing, or you draw a monkey and you show a picture of a monkey. Okay, you point to it. You don't define a monkey. You don't define a table. You point to it and you say, that's a table. That's how you teach your language to an ET Klingon, a little baby. You say, table. And then guy repeats, say, table. Okay, now he knows the word table. He knows what that noun is. You don't define, look, a table is that which has 4 legs. It's made out of atoms. And no, that comes later. That's a description. First, you point and name. Table. That's the way it works in physics. You got to point and name before you do anything else. You got to point to the ether. Then you can do whatever you want. You can move it, you can vibrate it, whatever. You got to point to the ether first, and so that people know what the word refers to. Okay. An object is that which has shape. By the way, yeah, concepts we define and objects we point to. An object is that which has shape. Okay. And that's the only property all objects have. That's a universal property of all objects. Concepts don't have shape. Objects do have shape. Okay. And the only way to introduce an object, again, is by drawing, by illustrating. Because if it has shape, you have no excuse not to draw it or to illustrate it. Okay? Okay, let's go with the second half of this. And here we get into the questions that a rational person is going to ask you if you propose the ether. Okay? Did I get that? Did I do that right? Let's see. Okay, we continue here. Proponents introduce and propose the ether as a medium. That's usually how an Aetherist presents he's insinuating, at least. Maybe he doesn't point to it and doesn't define it or whatever, but he's insinuating throughout his whole thing that he's going to be vibrating something. Except if you're Ken Wheeler, then you vibrate concepts, you move concepts around. But usually people are thinking in terms of particles. That's what the ether has always meant. Bunch of particles, okay? Therefore, they have no choice but to illustrate, point, and name. Okay? Example, here, a ball. Okay, here's a ball, and I point and say ball. Now the ET knows what a ball is. Okay, what I'm going to be using to do my theory with. Okay, the theorist must describe the ether before he moves anything. Okay, no motion yet. We're still trying to get an idea of what the object is before we move it. Quantum always says, quantum mathematicians, they always say, well, the electron is always moving. We don't know what it looks like. We don't know where it's at because it's always moving. Very simple. Just stop the universe for a second. It doesn't mean you have to look in there and find out what the electron looks like. This is not a question of experiment or measurement. This has to do with armchair physics. You lay back and you think. You use your brain instead of your hands or your eyes. You think and you say, what is an electron? For the purposes of your theory, we don't care what Mother Nature does in the real life because she's not explaining her theory. It's you who's explaining your theory. And if you're going to explain your theory and you're going to say electron, you better know what an electron is for the purposes of your theory. So if it's a little bead, call it a bead and show a picture of it and say, look, this is the Bowling ball, it's the nucleus, and this is the bead going around it. Now we understand. And of course, everyone's going to say, well, but that's not my atom. Well, sorry, then you need to work a little harder on your assumptions before you come and present a theory, an explanation, a mechanism. Okay, so next, the theory must describe the ether before he moves anything. He can go in there and say, look, this is the ether. He shows something. He points to something. Now he can describe it. He says, look, it's got this, this, and this, and that. It's got color. It's got smell. It moves like this. He can go on and describe it any way he wants. But first he's got to show the picture. Then he's got to describe it. And here are the questions that he was going to receive from an irrational individual. And that's what I give to all you thinking people out there, the few of you who remain on Earth still, okay? Is your ether infinite or finite? Tell me if it's infinite or finite. If infinite, what encapsulates the ether? Okay, I'm sorry, if finite, what encapsulates the ether? If your ether, is your ether a body of particles? Okay, is that what you're referring to? A body of particles, a bunch of particles as I call it? If so, what encapsulates each particle? What gives shape to each particle? Because there's some contrast there. You got to tell me what the black stuff is, what the contrast is. That's the key issue. Forget about your particles. Let's get rid of them. Just fine. And let's look at the black stuff and just analyze that for another 2 hours. If nothing, what do you mean by nothing? You can't say again, oh, nothing is the opposite of something, or it's the absence of something, or no, there are no antonyms allowed in science. Those are irrational theories. Those are people with little tiny brains who haven't spent the time to analyze the words that they're going to use to back their theory. And yeah, a lot of people want to get away from that and say, well, you're doing semantics. I want to jump to the theory. We need to lay the foundations of physics. And then is light a local, regional, wiggling, or is it the entire ether, the universal ether, which is vibrating? And if it's vibrating, vibrating against what? What's outside of it? Is it taking up space as it vibrates? Okay, and here's the final chart, okay, and here's a summary, and this is probably a better way of looking at this for you. Where is it? Here it is. Okay, this is probably more pictorial and it's easier to understand for a lot of people. You start with ether. Is it an object or a concept? If it's a concept, it doesn't belong in physics, period. Get rid of it. Is it finite or infinite? If it's infinite, it's not an object, it doesn't belong in physics. Get rid of it. Does it move or doesn't move? You got to tell us. You got to tell us if your ether moves or not. Is each particle, is the entire ether encapsulated? If not, it doesn't belong in physics. Just that simple. So it's that black stuff you got to identify no matter what. And you can't move concepts like Ken Wheeler does. You know, he moves concepts around and does a good job of it because a lot of people follow him because, you know, they like this stuff. They like esoteric, spiritual stuff. And that's why they follow him. And yeah, he's a televangelist for for so-called physics, science, if you want to call it like that. I just want to end with this, which are the foundations of physics. Okay, those who are interested, they can see it here. Let's put it here to the side. Okay, those are the foundations of physics. You need to define those words. He who cannot define those terms cannot even begin to do physics. He's not a physicist. You got to define what something is, what nothing is, and you can see they're antonyms. Okay, one is the opposite of the other, but not defined in terms of the other. Okay, I'm not saying nothing is the absence of something. Something is the absence of nothing. Not nothing. That's what something is. What's nothing? It's not something. No, not in science, not in physics. No, one is that which has shape, and nothing is that which doesn't have shape. Now you can use them consistently because now you know what something is and what nothing is. Okay, and concept. Okay, it's a word that invokes or embodies two objects or two words treated as object, like the word something requires nothing and something. We're treating nothing at that moment in time as a physical object. So we're saying there's two things there, okay? Two entities, two things that we're treating as an object, okay? It's a relation. You need to know what distance is, location, okay? You need to know the word exists because physics is the science of existence. Physics only studies that which exists. And of course, you need to know what motion is. We do not need the word time. Time is a word of religion. We don't use the word time in physics or in science. Time is a word very seldom, unless you use maybe qualitative, like before and after. I'm not sure how that would affect a theory. But if you're going to introduce numbers like seconds, years, or something, got nothing to do with physics. Okay, we don't use numbers in physics. Why? Because physics is about mechanisms. You have to explain a mechanism, not describe it mathematically with an equation. That's why we don't use math in physics. Let's that be clear. And otherwise, the onus is on the person to define what physics is. And I'm sure I can tear his definition into pieces, rip it to pieces. Okay. And for those who are interested, well, here I have what I call my test. You want to test yourself to see if you're a physicist. This is what you would have to pass. You would have to know uh, without any doubt whether any of these words represents an object or a concept. And you should be able to do them all. If you can't do them all, then there's something you still don't understand about the foundations of physics. Okay? So you would have to go through these words one by one, in your spare time when you're in the bathroom or when you're at the movies or wherever, and say, okay, is this an object or a concept according to the definitions of the foundations of physics? That which has shape, that which doesn't have shape, okay? Or, well, in the case of concept, it's nothing, it's just one more concept, but the definition is a word that invokes or embodies two objects or two words treated as objects. Okay, and with that, I don't think I have any more. I'll see you next time. Put myself back up here. So that's a wrap. Ether, a bunch of particles. Anyone introducing particles is introducing the ether. And so we don't care what the ether does, whether it moves, whether it vibrates, whether it goes straight. That's secondary. First, we have to identify what the word means. And if the word means bunch of particles, it doesn't belong in physics either, because at least as an object. You can't say the ether moved, the ether vibrated, because if it's a bunch of particles does not qualify as an object in physics. Bunch of particles is mereology. That's what it's known. In other words, parts of whole. We don't care about parts of whole. That's religion. That's what they do in Sunday school. A table is also parts of whole. What are you going to say? A table is a bunch of atoms, and then you say, oh, the table vibrated. Did the whole table vibrate? No, just a little piece over here. No, that's not a table. That's a piece of the table. And likewise with the ether is the whole shebang. But you say, no, but I'm saying it's a bunch of particles. Well, then that's not an ether. That's not a physical object. You can't say a little piece here vibrated and that's light. No. If you're going to talk about the ether, you're going to talk about the entire universe vibrating. And I mean vibrating as a whole, not over here and over there and over there. No, I'm saying that the whole universe is vibrating. You can't say the ocean vibrated because a little bit of water in the ocean was moved around by a fish. Are you going to say that that little bit of water that the fish, moved around, vibrated or whatever, is that the ocean that the fish vibrated? No, the ocean is the whole thing. And that's what you're doing with the ether if you say that the ether vibrated right here. No way. Not in science. Maybe in religion again. No, in science we do it in a different way. We first define the word. It's either an object or a concept. And the object is the whole shebang, the whole table. Can't say it's infinite because then you don't know it's a table. There's no such thing as an infinite table. But that's what these people say. It's the ether, it's infinite, bunch of particles. No way. No way, not in science. So study the foundations of physics. Study what an object is. See if you can identify which ones are objects, which ones are concepts. And I will see you on, Sunday. With hopefully I can get to this. I've been like 2 weeks waiting to get to them. Okay, we'll see you then. Bye bye.